PBR stands for physically based rendering. It is about the whole rendering environment and not just the shaders, but physically based shading is at its very core. PBR is the standard for realistic shading across platforms. The specific implementations differ, but generally they can be used in exchange. Opposed to PBR, there's also non-photorealistic rendering, or NPR. NPR comes in several different shapes and forms, and some of it can be abstracted from the PBR workflow, so I want to focus on PBR for this course. Like the name implies, physically based rendering is an attempt to accurately depict a rendered scene by describing it through its physical properties and simulating real physical interactions. For the shader, that means describing a material by the way it interacts with light. The great thing about PBR is that it breaks down the shader into objective parameters, which means that it will generally look accurate from all different lighting scenarios. Generally, what a material looks like is defined by its interaction with light, and there are different types of interactions that can be described with those physical properties. And those can then be given to a shader that translates the material for the render engine to use. In Blender, that shader is the principled BSDF, which is used as the standard shader for surfaces and has a lot of input parameters. Every one of these parameters has its own importance to the material, and changing only one of them at a time can have a drastic impact on the shader as a whole. Instead of the principled BSDF, you can also build a shader manually out of the individual shader nodes, but for this course we are sticking to the principled BSDF, as it is already the best choice for most regular PBR-based setups. For perfect realism, you theoretically want to have accurate maps for each individual one of these channels, as real surfaces generally have a combination of all different interactions with light, however subtle they may be. But usually, it is enough to focus on the most characteristic properties of a material to make it look convincing, and approximate the rest with constant values. Depending on the level of stylization you want, a more uniform appearance can even be what you are looking for. For the example scene, I went with more stylized PBR to simplify some of its complexity, but the principle stays the same. One thing about the render engines. For cycles, as it uses true ray tracing for rendering, the PBR maps simply influence how the simulated rays propagate through the scene. Eevee, however, has to approximate most of these light interactions using different techniques to fake the same look, and in most cases that works really well. The similarity of the result enables a powerful workflow with Eevee for preview and cycles for rendering. I will not go into the physical background of these light interactions, but let me quickly go over the different parameters in general. We will go over how to generate the different PBR maps in a procedural workflow in the following videos. The base color is, like the name suggests, the main color map that the shader is based on. It describes the color of the diffuse, metallic, or transmissive light interaction. Ideally, the texture map used here should contain no light information like shadows and highlights at all, making it what is called an albedo map. Then, all the shading comes from the actual geometry and light sources in the 3D scene. If, however, the geometry is lacking the relevant amount of detail to produce this light information while rendering, which is the case most of the time, it can be useful to include some amount of lighting in the base color already. A color map that includes some lighting information like shadows and ambient occlusion is called a diffuse map, and it helps to add realism to objects with a low poly count, when highly detailed displacement is not an option. In this example, you can see how the diffuse map adds more depth to creases that are not showing on a geometrical level. So you have to make the conscious decision whether or not you want to include lighting information into the base color map. With procedural shading, it is more straightforward to create an albedo map, as the lighting information comes with the rendering. From photographs, on the other hand, it has to be carefully extracted or avoided. While we are on the topic, I want to also talk about the shader displacement. Shader displacement is not part of the principled BSDF itself, but can be accessed through the displacement socket in the material output node. Cycles supports the option to displace the mesh on a shader level when rendering. That way, you can add additional geometric detail from within the shader editor using a displacement map generated just like the other PBR maps. What this displacement does is exactly the same as the displace modifier, Only here, you can use the shader nodes to drive how the mesh is displaced. That can be extremely useful to create highly realistic surface detail and also general procedural shapes based on the shader. However, to be effective, the mesh has to be highly subdivided, which drastically increases memory usage and render time, and it is only available using cycles currently. As you can see, the socket accepts a vector as the type, which means that you can technically displace any point on the mesh in any direction, allowing you to effectively change the complete shape of the geometry from within the shader. This, however, has, besides from looking very fancy, only rather few applications and is quite advanced and difficult to control. So, for the scope of this course, we are going to focus on the single-dimensional displacement using a height map. And maybe at the end we can throw in vector displacement as a bonus. Let's move on to the next inputs of the principled BSDF. Subsurface scattering describes light penetrating the surface and being scattered beneath it, creating a glow where the light hits. Subsurface scattering can be very crucial for different material types, like for example skin, and add more depth and life to materials. But this type of light interaction depends highly on the geometry of the mesh and has to be simulated with a lot of rays to be accurate, which creates a lot of noise. Because of that, subsurface scattering only produces accurate results using cycles and has to be faked when using Eevee to work in real time. There are 3 maps to control the subsurface scattering in the principled BSDF. The subsurface input simply blends between the simple diffuse and the subsurface scattered shading as the base shader. They both also use separate base color maps. For the subsurface scattering, this can be plugged into the subsurface color socket. The third map is the subsurface radius, which determines the distance the light is scattered underneath the surface, and thus changes the softness of the subsurface effect. This input accepts a vector, which makes it possible to tint the scattered light by defining a different scattering length per RGB channel. The shorter this radius input, the more it converges to the diffuse shading. There are also different algorithms that can be chosen to simulate the propagation of the scattered light. The metallic input blends between a base shader that is using diffuse and reflective light interaction. Those behave fundamentally different, so usually it is a good idea to map the parameter's value to either 1 or 0, depending on the class of the material, and only use values in between to transition between them. Because they behave so differently, the metallic input influences the behavior of the whole shader. A lot of these parameters only influence the non-metallic part of the shader, so for the showcases here, I will focus on other materials. The specular input controls the reflectivity of the surface. This reflection happens on top of the base shader, and its intensity depends on the viewing angle. Also, it is not based on the base color unlike the metallic reflection, but it can be optionally tinted using the specular tint parameter. Usually for a PBR shader, keeping it on 0.5 yields good results, as all real materials have a certain amount of reflection to some capacity. The parameter you should mainly focus on to control the reflection is the roughness. The roughness parameter controls exactly what the name implies. It is a measure of the roughness of the surface on a microscopic level, and it is used to simplify the surface detail so that not every microscopic little bump has to be described, but the roughness of the surface as a whole. The nuances in this map add a lot of character to a material, and getting it right is one of the keys to a convincing PBR shader. Anisotropy is another parameter that gives information about the microscopic detail of a surface. An anisotropic reflection occurs whenever part of the surface is structured with a preferred direction. That results in the reflection being wrapped around the geometry depending on that direction. The most prominent example of the use of this effect is brushed metal. The rotation of this preferred direction can also be tweaked with a parameter. And the fact that this preferred direction has to be wrapped around a 3D surface creates a pole where the directions run together. The way this is oriented can be accessed using the tangent input. Sheen is an effect to add a highlight depending on the angle of the surface that can be used to create more fuzzy-looking materials like cloth. This effect can also be tinted by the base color. Clear coat adds an additional layer of reflection on top of the shader. Usually, this is used for surfaces like car paint that have a glossy finish, but the roughness of the clear coat layer is fully adjustable as well. The transmission parameter controls how much light passes through the object to create glass-like materials. How blurry this transmission is controlled by both the surface roughness of the overall shader and additionally the dedicated transmission roughness. The IOR parameter also impacts the transmission. IOR stands for Index of Refraction, and it is another intrinsic material property that tells the refraction of the light when it's transmitted. The emission map is a simple emission effect that is added on top of the shader to create a glow. The fact that it is added means that an emission of 0 or black adds nothing. The input here is a single color input, but for highly emissive materials, the values can also surpass the range of 0 to 1. The alpha input is a parameter to control the opacity of the surface without influencing the shading itself, but rather blending the shaded surface with the background as a whole. The normal input takes into account the surface detail that falls in between the microscopic scale, where it can be translated into roughness, and a large scale, where it is geometrically significant. It directly controls the normal direction of the surface and can this way add visual detail to the shader without the need of a highly subdivided mesh, like it is the case with displacement. The normals of the clear coat layer can be controlled separately to keep surface detail while adding a smooth finish.